Welcome to the HIL Python API video. In this video, we will demonstrate the possibilities of the HIL module, which enables us to execute script-defined test sequences. We're able to do this using the HIL Python API. It allows the user to control all the aspects of the HIL toolchain using the Python programming language. Let us first clarify the differences between manual and automated toolchain settings. In the first scenario, the user manually sets system parameters, PV curves, input voltages, motor loads, analog output gains and offsets, etc. With the Python API, the whole process is automated. In this video, we will see how the user can define an arbitrary load profile and test a motor drive in the case of a lost phase voltage. Let us now examine the power electronics system in detail. A two-quadrant motor drive with an induction machine, inverter, DC link and rectifier is connected to the electrical grid. All the elements of the electrical circuit are intuitively drawn with the HIL schematic editor using components from the HIL library. The power stage is emulated by the HIL 600. The control algorithm is based on the classical indirect field-oriented control, IFOC, which is implemented on industrial controller, a Texas Instruments F2808 DSP. The HIL docking station is used to interface the TI DSP with the HIL 600. Let us now start with the tests. In order to do so, we open the script editor. Here, the users can define their own tests using the Python programming language. We've prepared one such script to illustrate the concept. We will test indirect field-oriented control algorithm implemented on the TI DSP with a sequence of step and ramp changes in the motor load. In the second part, we will test the system response in the case where the loss of one phase voltage occurs. Of course, all settings such as allocating analog outputs and digital inputs, which are needed to close the loop, are defined from the Python script with their gains and offsets. All Python functions used in the HIL Python API are described in the dedicated Python API documentation with illustrative examples. Let us now run a prepared Python API script. In this test, the whole process is automated, including model compiling. We choose to observe the machine current of phase A, as well as machine speed and torque. Remember, for the first test, we will apply the load profiles shown here and repeat it 6 times. We press Enter and continue. We see the consecutive changes of torque between zero value, step change and ramp change, while the motor mechanical speed has shown transients due to load change. However, it remains regulated at the defined level, which means that controller implemented on the TI DSP is properly designed. The first test is over. Now the second test with the loss of phase A voltage will be performed. Here, 3 signals will be observed: phase A voltage, machine electrical torque and DC link voltage. Phase A voltage will be reduced to 0 and restored to the full value every 3 seconds. The sequence will be repeated 6 times. Please notice the increased ripple in the machine electrical torque and in the DC link voltage due to the loss of the phase voltage. Of course, we can continue testing our controller under all imaginable conditions, such as injecting sequences of harmonics, emulating faults, applying different load profiles, etc. Using the HIL 600 with the Python API, we're able to automate the process until we are satisfied with the controller's performance under all conceivable conditions, thus greatly increasing quality assurance.